So this is my third video on strophoids, and I want to talk about how a strophoid arises from a construction with a complete quadrilateral. A complete quadrilateral is basically four lines in the plane, any four lines. But I want to, in this particular case here, consider only quadrilaterals that have an incircle. Okay, so they circumscribe a circle. Now, in GeoGebra, for one to construct a generic quadrilateral that circumscribes a circle, you basically just need to draw a circle. Its center is here on N, just to use the notation we used in previous videos, because this is going to end up being the node of a strophoid. I just select four tangent points on the circle, and I have a complete quadrilateral here that has this incircle. Okay, now I want to also remind us of the concept of this internal limiting point of the quadrilateral, which is the midpoint of these two internal diagonals, and the external limiting point, which is basically the foot of the diagonal of the perpendicular drop from L sub I onto this external diagonal. Okay, so the external diagonal connects these two outer intersections of these four lines. There's a total of 6 intersections. So now you have this construction, and we're just going to keep this in mind now for the time being. Okay. Now the next thing is I want to talk about the Newton line of a complete quadrilateral. This is a well-known object. Let's go ahead and light up the Newton line if I can find it. Before I light up the Newton line, I want to talk about the three midpoints of these three diagonals here. So I have a first diagonal, a second diagonal, and a third diagonal. So let's light up their midpoints. Okay, let's find them here. So here's the first midpoint, this one here. Let's call this guy M1. Then I have a second midpoint. Let's call this guy here M2. And then I have a third midpoint out there, and let's call this guy here M3. Now the Newton line, and Newton is credited to this observation that these three midpoints are collinear, and the line that connects them is known as, at least in some circles, the Newton line. Now notice that if our quadrilateral circumscribes a circle, the Newton line also goes through the center N of the circle. Okay. Now it turns out that this line is very useful for us here, because if I actually light up, so if I'm interested, let me say it like this, if I'm interested in inconics to this quadrilateral, what is an inconic to this quadrilateral? Is a conic which is tangent to the four lines that you see on the plane here. So for example, the incircle is a valid inconic to this quadrilateral, but there's a one-dimensional family of such inconics, because a conic requires 5 constraints. If I'm saying be tangent to 4 lines, there's going to be one degree of freedom that is loose. And as it turns out, the Newton line is the locus of the centers of this 1D family of inconics to this quadrilateral. So let's go ahead and show a point on this line, which I believe here, I have. Let's see what I call it. I call it P. So there is P, and I can set P anywhere on this line. And what is neat is that once I define P, and I say now I want an inconic centered on P, tangent to these four lines, the inconic is unique. So for example, let's draw one inconic here. This one, it's an ellipse, right? And as I move P, I get a different inconic. So you can see here, you can investigate how the type of conic changes as I traverse these midpoints of the three diagonals that lie on the Newton line. So as I travel, so in this region here, my inconics are ellipses. You can see here that this ellipse is tangent to the four lines of the complete quadrilateral. But as I cross over M3, it becomes a family of hyperbolae centered on P. And as I cross the second midpoint, M2, it becomes a family of ellipses again, and these ellipses become congruent with the incircle if P is on N as expected. And as I keep going forward, I become an ellipse again. And then as I cross M1, once again I'm a family of hyperbola. Okay? Now this phenomenon put aside, okay, what I want to show you guys is what happens if we track the motion of the foci of this family of inconics. So now I need to find the foci. They're here. Here's F1 and here's F2. Okay, so as I move the inconic, the foci move as well, right? You can see that this first F1 is passing to that outer L sub B limiting point of the complete quadrilateral. So now let's light up the locus of these foci over all centers on the Newton line. So I have that somewhere. There it is. And beautifully, the locus of said foci happens to be a strophoid with node at the center N of the incircle and a focus that we're going to have to locate. But notice the first phenomenon. The locus goes through LE, but it does not go through L1, L sub I. Now, as it turns out, these 2 points are inversions of each other with respect to the incircle. Okay, so if I invert L sub I on the incircle, I get L sub B, and vice versa. So remember what I did on video 2 on strophoids. To locate the focus of a strophoid, we need to go through that inversive image of the strophoid, which is a hyperbola. So let's go through the steps. To build a hyperbola, I need 5 points, right? So let's see, I could invert the 2 foci, that gives me 2. I could invert L sub B, which gives me L sub I, that gives me 3. We know also that it's going to go through N, although its inversive image is in the line of infinity. So I have 4. So now I need a 5th point, and I'm going to just select a point on this locus curve. It's a little bit unstable when you do this with GeoGebra. But now I'm going to invert, so let's go ahead and reflect about circle all these points. So I'm going to do reflect about circle. So I'm going to reflect F2 about the incircle, and I could have chosen any old circle to reflect them upon or to compute these inverses. But the advantage of using the incircle is that Li is guaranteed to already be on the hyperbola because it's the inversive image of L sub B with respect to the incircle. So I've inverted F2. Now let's invert F2 with respect to the circle. Now let's invert this point with respect to the incircle. And now I have 5 points. So let's try to run a conic through these 5 points. So help me God. I'm going to go, so we know that the conic goes through N. It goes through the inversion of this point that I put on the curve. It goes through M, and it goes through the inversion L, which is one of those 2 foci. So there's the conic, the 5-point conic. Okay, if I move this point on the curve, you can see that the conic doesn't change. Now, as I have done in the previous video, I'm going to color this conic to facilitate visualization as a blue rectangular hyperbola. Okay, and we know that this guy here is okay, so I'm going to call this guy here F sub 1 prime because it's the inversion of one focus. This guy here is the inversion of the other focus, correct? So I'm going to call it F sub 2 prime. Okay, there it is, barely visible. I can hide these labels of, I can actually hide the objects, right, from my Newton line. Let's hide them, no longer needed. Okay, so now I can see that I have a 5-point conic, 5-point, in this case, rectangular hyperbola, because that's a property of all strophoids. The inversive image of a strophoid with respect to a circle centered on its node is a rectangular hyperbola. And then using Arsenis Akopian's algorithm, I'm going to locate now the center of this conic. So I'm going to have to type center E. There it is. Beautiful blue dot, perhaps. Yes. And remember, what I need to do now is I need to reflect the node upon the center. So I'm going to say reflect about point, reflect the node about the center. And whatever I get here is the inversive image of the focus of my strophoid with respect to this circle here. So I need to reflect. So let's call that N prime point there. I'm going to call it, just for fun, F prime, because it's the inversive image of the focus that I'm looking for. So now let's reflect this guy here about my incircle. No, not this one. this one. Got me the wrong guy. I want to reflect about circle point f prime with respect to this circle here. And there is f prime prime, which I'm going to call simply f if this doesn't break GeoGebra. Okay, there you go. So now we've effectively used Arseny's algorithm. You can see that these 4 points here, the center of the hyperbola, which I'm going to call, let's call this guy here O sub h. Okay, let's put a label on it and let's take a look at it. We can now see that, oops, I don't want this guy. I just want O sub h, which is over here. And I'm going to make this collinearity line here be dotted. I'm going to make it be gray. And we can see that these 3 points here, or 4 points rather, n, the center of the inversive hyperbola, the reflection of n upon the center of the hyperbola f prime, and f are all collinear. And this is giving me a coordinate-free method to locate f. Now notice that f is somewhere over here. If I move this quadrilateral around, okay, I can see that f can be made to approach L sub e. Okay, so the final observation I want to make here is a missing link with, we know that this quadrilateral contains an incircle. Does it contain a circumcircle? Is it circumscribed by a circle? Let me say it that way. So I'm going to make a circle passing through these 3 points here. And I'm going to make the circle be, let's pick a good color. Okay, brown maybe. Here's a brown circle. Now you can see here that this is not a bicentric quadrilateral because it doesn't have a circumcircle. It does have an incircle, but not a circumcircle. So I'm going to just play around with these tangents here until I come up with until I obtain something that looks like a bicentric. Oops, I just don't want to make this guy be unstable, so perhaps I can move here. You have to be careful here because this can be unstable. So there you go. Now I've just adjusted these 4 tangents here on my complete quadrilateral so that I have a circle now, and now I have a cyclic quadrilateral, right? It has a circumcircle, the brown one, and it has an incircle. The miracle that happens here, or the property that happens here, is that f, only in this condition, the focus of my strophoid coincides with the inversive image of my inner limiting point, the midpoint of these 2 diagonals, and the reflection of n upon the center of the hyperbola also seems to coincide, and this must be the case, with the internal limiting point, right? So this is a property of bicentric quadrilaterals, that you have these coincidences, f and f prime coinciding with L sub b and L sub I. But if the quadrilateral is not bicentric, it doesn't have a circumcircle, then you can see here that f, the focus of my strophoid, and that outer limiting point, L sub e, do not coincide, nor do f prime and the inner limiting point. Okay guys, so that's all I have for this video. Here's a strophoid being generated as the locus of foci of a family of inconics to a complete quadrilateral with an incircle. See you on the next video.